So now that we have done alkane naming and alkane structures, we're going to move on to our next family or functional group. So we've been talking about molecules that have all of their carbon atoms bonded to the maximum number of atoms. And we call these saturated hydrocarbons, alkanes. Now, we know it's possible for molecules to have double bonds or even triple bonds. And the naming and process around these molecules stays more or less the same. All we really have to understand is a couple changes in how we count the carbon atoms and a couple other things that are a little bit different but not very much. So any atom that has a double bond in it has what we call an alkene group or a functional group, an alkene functional group. As soon as there is one double bond, that means that there isn't the maximum number of atoms, so we call it an unsaturated hydrocarbon. And again, this word probably is familiar to you because it is used to saturated and unsaturated fats in nutrition. Alkenes are considered aliphatic because they do not have benzene attached to them, but they are relatively predictable. They are reactive, so they will react with things. Things can be added to the double bond, opening it up, whereas alkanes don't have any double bonds, so are generally very, very unreactive. Alkenes have a general formula of CN2N, which is comparable to our alkane formula. And the process we get an alkane turning into an alkene is more or less straightforward. So here is ethane, C2H6. So what needs to happen is two of these hydrogens need to take one of their electrons and leave. And we can represent this. Let's just draw it out for a second. We can represent this with just dots rather than bonds. So this is exactly the same drawing as below. It's just we're showing dots to represent the lines. When hydrogen decides to leave, it's going to take one of its electrons out with it through the process called an elimination. These two electrons that are left over will want to find each other and form a double bond. So we end up with this. And when we can also just symbolize this as just a straight line with a double bond on it. But that is essentially what happens, and that can happen over and over again. To make an alkyne, just another two of the hydrogens will also perform an elimination. Elimination being the removal of substituents and then creating a double bond. So this generic formula that we're talking about, of course, reflects this. So I have 2 carbons and 4 hydrogens, which is what that means. This is only true for one double bond. You have to take away 2 hydrogens for every additional double bond that you have. So that takes us down to nomenclature. So the nomenclature of alkenes is very similar to alkanes. It's just really on how you number it. So the big difference would be is you always start numbering as close as you can to the double bond. So in a molecule like this, The double bond is closer to the left side than the right side, so I would start numbering here. That's really the biggest difference. And then the suffix will change to "ene" from "ane." Just a really quick summary of how to name them. We'll do some practice naming. It's still prefix, root, suffix. It's exactly the same. We change our ending to "ene." So you find the longest chain, and the longest chain that contains the double bond. You could potentially have a chain that was long but didn't include the double bond, and that would not be the proper route to use. Change the ending to "ene," and then number from the end closest to the double bond. Identify the branches just exactly the same as that you did with alkanes, and then put it all together. So here's two molecules that we can practice with. So we first have to find that root. So there's the double bond. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So this side way has more branches, so we'll pick it. Just like we did before, we have a methyl, and 2 carbons is an ethyl. We have two ways that we can number, from the left or from the right. If we number from the left, the double bond gets a smaller number. So we'll do that. When we're describing where the double bond is, we always use the lower of the two numbers. The double bond occurs between carbon 3 and 4, so we'll identify it at 3, not 4. Then we simply put it together. So I have 2 methyls in 1 ethyl. So alphabetically, ethyl comes first. So 3 ethyl hyphen. I have methyls both at 2. Don't forget our dimethyl. So 3 ethyl, 2, 2 dimethyl. So I've taken care of the prefix. Now the root for 7 is hept. But before we get there, we have to put that number in for the double bond. So 3 hept is the root, and the ending changes to "ene." So 3 ethyl, 2, 2 dimethyl, 3 heptene would be the correct name for this. So looking at this one, the chain looks more or less the same. It's the same structure, just the double bond has moved. So there's our double bond in the longest chain. Number our carbons. Clearly the double bond is closer to that end, so that's where we start numbering. I still have a methyl. You don't have to write these out in front of it, but some people like to see the chains identified. So it's the same beginning, except the prefix numbers are different. So now it's 5 ethyl, 6, 6 dimethyl, takes care of those. 1 heptene would be the correct name for it. So really the numbering is the biggest difference, and then obviously the suffix as well. Everything else is the same as alkenes. Just remember that you've got to include the double bond in your longest chain, and you have to make sure that you number closest to where that double bond is. If there is a tie, depending on which direction you were to go, the tiebreaker would be the branches. So you want to still try and give those branches the smallest number possible. So if you can do that based in one direction versus the other, then do that. That would be your tiebreaker. So this is a pretty good chance for you to pause and practice. Take a minute and go through try these. And as you do that, just either if you get stuck, hit play, or if you are done and you want to check your work, just hit play as well. So for A, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So it doesn't matter which way we number it. I'm just going to do left to right. There's no branches on it, so it just becomes 3 hexene. We got to get that double bond in there for B. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So there's our main chain. Double bond is closer to this side. So I'll number closer to that side. 3 carbon chain is a propyl. You have that chart handy, hopefully. So we have a propyl at 3. We have a double bond at 2. Put your root, it's 7 carbon, so it's hept, and the ending is ene. This one's potentially a little bit trickier, so it's got to include this. So 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 2, 3, 4. So this has got to be the chain. Make sure your double bond is included. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the double bond is exactly in the middle. We'll number from this side, giving those branches a smaller number. We have an ethyl here and 2 methyls. So I have an ethyl at 4. Ethyl is going to come first alphabetically again. I have a 2, 3 dimethyl. Double bond occurs at 4. The root is oct. The ending is ene. So as you can see, it's very, very systematic as you go through them. Just draw a condensed structural diagram for each compound. 2-methyl-1-butene. So it works the same as alkenes. Those are alkanes. So find your roots. That's 4 carbons. 1, 2, 3, 4. The double bond is at 1. So we'll create that. Again, you get to place your numbering wherever you want. And at 2, I have a methyl. Fill in with hydrogen, so I have 2 bonds. I need 2 more to get to 4. 1, 2, 3, 4. No hydrogens. 2. So remember to make sure every carbon has 4 bonds. So that would be 2-methyl-1-butene. This one is 5-ethyl, 3,4,6-trimethyl-2-octene. So again, identify your root. So I have 8, 1, 2, 3, 4, 5, 6, 7, 8. I have a double bond at 2. I have methyl groups at 3, 4, and 6. There's really no reason to put them above or below. It is completely irrelevant. And at 5, I have an ethyl group. Again, just literally writing these alkyl chains directly off my table. And now finally, we just fill in our hydrogens, so every carbon has 4. So 1 bond, I need 3 hydrogens. 1, 2, 3, I need 1, 2, 3, 4, 1, 2, 3. Number 2 says draw different structural isomers of C4H8, an alkene. So 1, 2, 3, 4. I'll put the double bond here. So the double bond could be there. 1, 2, 3, 4. Or it could be in the middle. We can't put it between the last two because that will be the same as here. So this is 1-butene, and this is 2-butene. Because numbering is based on what end the double bond is closest to, if you put it here, you'll still end up with 1-butene. You'll just have to number in the opposite direction. So now we have to talk about geometric isomers. So the first type of isomer that we've talked about is called a structural isomer, and that is when the double bond is in a different spot, or if it's the same formula, just rearranged differently. For example, if there were a branch here, the chain was shorter, but there were more branching, and it had the same chemical formula or the same molecular formula. So let's look at butane here. I am missing a hydrogen, but it will serve our purpose. So the thing is with butane is I can set it up in this configuration, and basically chemically those are the same. It'll probably not want to be like that because of repulsions, but the thing is with bonds is you can have rotation as long as the bonds are single bonds. What causes a problem is when we have to move to double bonds. So to create a double bond, we just quickly adjust this molecule a bit. So when a double bond is created, the first thing we're going to notice is that, yes, you can still rotate around the single bond, but this is now unable to rotate. Let's put our methyl group back on here. I have an extra carbon now, but that's okay. And when we start to look at this, 1, 2, 3, this carbon only has 1, 2, 3 bonds. So I'm just going to add a hydrogen here. And when we start to look at this molecule, that creates a little bit of a problem because right now I can't rotate this hydrogen away from this methyl group because it's a double bond. And what that means for us is that because I have this problem, let me just make this hydrogen a little bit more explicit. Because I have this problem, it means that when I have two hydrogens on opposite sides of the molecule, they're going to stay there. And chemically, if this were a single bond, they could just rotate, but because it's a double bond, they can't. So the thing is, with the geometric isomers, is we have something that is chemically distinct from the opposite one, or if the methyl group is turned down and both hydrogens are on the same side, once again not being able to rotate. So what that does is it creates a problem that we have to be able to name. And how we name it is we call it cis and trans isomers, or geometric isomers. And that is very different than structural isomers. So in order for a cis-trans isomer to exist, you first of all must have a double bond. That's the first must. The second thing that needs to happen is on each side of the bond, so ignoring what's under my hand, these groups have to be different. And then on the other side, these groups have to be different. So the longest chain, if I'm naming it, is still along the black balls there. But that's the first thing. So I do have a geometric isomer here. So the question becomes is how do I name it? So there's two different types of configurations. The first configuration occurs when we have our large group. So this is the 2-carbon chain and the methyl group. So this is kind of an ethyl group and a methyl group. They're not branches, but that's just how I'm going to refer to them. They're both on the same side of the molecule, or the hydrogens are on the same side of the molecule. And what that creates is both hydrogens are said to be cis to each other. So when we have, more importantly, the two large groups, the two heavier groups on the same side as we do here, this big group and this big group, we say that this molecule is a cis isomer. That is opposed to what we started with. That's like this, again, no rotation, where the hydrogens are on opposite sides of each other. Again, still the same, different groups on either side of the bond. And we say that this is trans to each other. So it really is important that we identify that because, again, it's chemically distinct. It's chemically different. So let's have a little bit more of a look at how we name these things. So just a couple little notes. It says to have a cis-trans isomer, each carbon in the double bond must be attached to two different groups. We talked about that. The cis, the two larger groups are on the same side, and the trans, the two larger groups are on the opposite sides. And again, they have very different properties from each other. So to give you an example, cis-2-butene boils at 4 degrees Celsius. Trans-butene boils at 1 degree Celsius. It's not a big difference, but it is a difference. The melting point, this will melt at negative 139 degrees Celsius, and this one will melt at negative 106 degrees Celsius. So again, they're different. If I buy them at the store or I buy them at a chemical supplier, it will matter. So we look at this molecule. The biggest red flag you'll get for cis and trans being involved is when hydrogens are drawn in, and we say they're explicit hydrogens. The explicit hydrogen drawn into a structure usually is trying to identify that we might have a geometric isomer present. So when I look at the bond, we're first going to let's just name it like we normally would. Do our longest chain, number, so 2-hexene is the molecule, and this is 2-hexene as well. Here's a heavy group on one side, the big long chain is the other one, on opposite sides to each other, so we say trans. They're on the same side in this one, so this is the cis isomer. That's really the big difference here. We're not going to go into a lot more detail with this. When we start talking about geometric isomers, it leads into something called optical isomers, and it does get a lot more detailed, but for right now, this is just good to recognize that on long double bonds, because there's a lack of rotation, we do have this form of isomer created. So what we're going to do now is we're just going to go through a couple practice questions, and while you're doing that, just take a pause once again, and if you get stuck, then hit play. So it says draw and name the cis-trans isomers of C5H10. So I'm going to do line diagrams because I find that easier. So 2, 3, 4, 5. So there's 1, 3, 4, 5, 1. So again, those are two structural isomers for the molecule. Again, if I put the double bond here, it's the same as this one, so it doesn't really help us. You cannot have a structural isomer at the end, because if you do, you have two hydrogens which are the same group, so there's no cis-trans isomer involved here. On this one, however, I could have the hydrogens on opposite sides and the big groups on the other. So this one will generate an isomer. So we have two different forms of isomer. We have cis and we have trans. So we'll do the trans one first because we already have it done. 2, 2, 3, 4, 2, 3, 4, 5. Double bond, hydrogen, hydrogen. This one becomes a little bit stranger for you, but it becomes the cis again on the same side. So realistically, all I've done is I take those lines and I switch what's on them, and I just don't write in the methyl groups. We can do the exact same thing for C6H12. So 2, 3, 4, 5, 6. So I have this structure, 2, 3, 4, 5, 6. This structure, 2, 3, 4, 5, 6. And this structure. So 1, 2, and 3 hexene are created. We know that because of the same reason for here, that this is not going to generate any. So we're going to end up with 2 structures here. So cis and trans. So when we go to do this, I'm going to draw a condensed form for right now. 6, 1, 2, 3, 4, 5, 6. So again, this would be how I would draw the cis isomer. Again, just follow my longest chain, and I'm drawing it out to show that there is an isomer present. Let me do the same thing for trans. Start with the same root. And then show your hydrogens on opposite sides. So there's your cis and trans isomer. So we'll do the same thing. I usually just start with the double bond. I have 2. One, 2, 3, 4, 5, 6. Hydrogens on the same side. There's my cis isomer. And then I'll also do trans. And put my hydrogens on the opposite side. So there's 1, 2, 3, 4 geometric isomers, and then I still have the 3 structural ones, where this one, because the hydrogens are the same molecule on the end, it doesn't really matter. So lastly, with the try this, the big thing we're going to look at is whether or not they have structural molecular geometric isomers. So for this one, again, it's at the end, so we know it doesn't. This one, I look at each side of the bond. Those are different. Those are different. So yes, I do. We'll draw the other form. Just keep one side the same, so I drew it exactly like that. And then I just draw the other form. So this is cis, and this is trans. For C, there's no double bond. So no, there's no double bond. Again, D is moved over. The formatting's a little weird, but once again, look at the double bond. Different, different. So this is the trans form. And now we just draw the cis. There's my cis isomer. So again, notice that I've just moved where the hydrogen and methyl groups are. And that's really all you have to do for cis and trans isomers. When you're asked to recognize them, you need a double bond, and you need to have the different groups on either side. So that takes us to our third family, or third functional group, which is alkynes. So alkynes are just triple bonds. It's really not different at all. The ending changes to -ine, and the general formula becomes CnH2n minus 2. We end up with a couple molecules here. This is common. This is the common name for this molecule. It's acetylene. We would actually call it Ethyne. Acetylene is usually used in welding. And once again, propyne as well. So when you're naming, everything's the same as you're doing with alkenes. It's just the ending of the suffix is different. So just to show you what I mean, there's our longest chain. The triple bond is closest to this side. I have 2 methyl groups, so 4 dimethyl, 2 pentyne. Again, the ending being different is the only thing. You can take a second and try the next one. Just pause and then we'll go over it. So with this one, we just make sure that once again the triple bond is included. So I know that part is at least has to be in the chain. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm just going to take the straight one just to make life easier. Number. So we have a propyl. I'm just going to write them out because we have 3 different ones in here. So remember, your branches go in alphabetical order. So ethyl, methyl, then propyl. So I'll just write it up here. It'll give me a little bit more room. 3 ethyl, 5 methyl, 3 propyl, 1 hexene. Again, big difference just being the ending. So that's really the second group of functional groups. Alkenes and alkynes have exactly the same priority. We will talk about tie breaking and what happens when both are present or multiple double or triple bonds are present in the same molecule. But the basics of naming really are the same. The second thing that we should have gone through, you should hopefully understand a little bit more now, is the idea of geometric isomers.